Hello, Duhawks, and welcome to Unit 3. In this unit, we're going to be talking about fuel for exercise in a process known as bioenergetics. And bioenergetics, essentially what we're talking about is how we can take fuel and break it down to be utilized within the body in a form of energy known as ATP. Now, I will warn you, this is probably the most sciency or most technical unit that we're going to cover within this course. So please don't be intimidated. Please make sure to pause the video and take good notes. Please reach out if you do have questions about these words, these processes, how this all kind of works together. I'm happy to help in any way that I can. So let's start with some terminology. So when we think about energy and bioenergetics, the first kind of term that we want to talk about is something known as a substrate. And a substrate is going to be, think of this as kind of like your base product that we need in order to get energy. So we have kind of three options for substrates. These are going to be, like I said, the fuel sources that we are going to make energy from. And that energy currency within the body is something known as adenosine triphosphate, or ATP for short. Okay, so this ATP, think of this as like the dollar bill within the body. And these ATP dollars are going to be used to do all sorts of different things that require energy, both exercise and other processes within the body. So our three kind of options in terms of where we're going to get these fuels are the calories that we consume, and those will come in three different forms. We have carbohydrates, we have fats, and we have proteins. And we'll talk about kind of the differences in terms of, how we might use each of these in various elements within the world of exercise and within the body as it relates to something known as metabolism. Okay, so we think about bioenergetics. What are we talking about here? Again, this is simply the process of taking these substrates, so taking your carbs, your fats, your proteins, and how can I put them in a form chemically that will allow me to use them as a fuel source, or taking carbs, fats, and proteins and breaking them down into usable energy within the body. Okay, so this is going to be performed at the cellular level, and we'll talk about the three different kind of energy systems that we can use within the world of bioenergetics that will allow us to break down and utilize those three substrates. And metabolism, this is a term that's thrown around a lot, a nice buzzword in our pop culture, I would say. You can talk about, people have a high metabolism, low metabolism. What does that mean? Essentially, we're looking at the sum of all of those energy needs within the body, right? So somebody who has a high metabolism is going to burn a lot of calories. So they're going to need a lot of these substrates. They're going to need a lot of carbs, fats, and proteins in order to fuel those different processes within the body. Okay, people with a low metabolism maybe don't need as much of these substrates. Their breakdown process or those bioenergetic pathways are going to work a little bit slower than somebody with a high metabolism. But essentially, we're looking at the sum of all of those energy needs and all that energy breakdown within the body in order for us to kind of understand how much somebody might need or how much somebody might use within a given day or within a given exercise task. Okay, so we think about substrates. Again, these are going to be our fuels for exercise. And as we mentioned, three different options here. We've got our carbohydrates, we've got our fats, and we've got our proteins that are all going to provide us with energy needs in order for us to produce ATP. Okay. And again, when we look at, or when we kind of zoom in on these products from a chemical perspective, they will contain carbons, hydrogen, oxygen, and nitrogen in order for them to be chemically structured. Again, we'll talk more about this in sports nutrition. If you haven't taken that class yet, we'll kind of dive into the nutritional element of the carbs, the fats, the proteins, and kind of how that all works. So essentially what we're talking about, we're going to take energy from the chemical bonds of these items, and those are going to provide us with that high energy compound and allow us to, like I said, use these different pathways to produce ATP, which is kind of like our energy currency or our dollar bill within the body. Okay, so we think about fuel for exercise. Let's kind of take a look at kind of some of our options here. Okay, so at rest, we're going to use about 50% carbs and 50% fats for our fuel sources. Again, resting metabolism or resting metabolic rate can vary substantially from person to person. Again, if you're working with, let's say, high school boys, for example, very high metabolic rate at rest. And again, we have to think about some of the other kind of unique characteristics of that particular population. They're probably still growing. They are gaining muscle mass. All of those factors are going to contribute to metabolism. As we age, metabolism will slow down. That really doesn't happen until like mid 30s. So again, if you're working with high school and college aged athletes, we're probably still pretty good in terms of that resting metabolism in terms of the total amount, right? But regardless of your age and regardless of how high your metabolism is, at rest, we're about 50% carbs, 50% fats for, those fuel sources. Okay. During short exercise, we're going to use mostly carbohydrates. So again, if we're looking at exercise that's 30 minutes or less, carbohydrates are going to be kind of our main fuel source in those scenarios. For longer exercise, again, think over 60 minutes in duration, we're going to rely on a mixture of carbs and fats. Really kind of when we think about this from a general perspective, again, carbs are going to be the main fuel source for high intensity exercise and for exercise that's short in duration. Like I said, 30 minutes or less is pretty much all carbs. As we kind of increase the duration of that exercise, so as we get to 45 minutes to 60 minutes, we're going to start having more of a contribution from fats in terms of that fuel use. And again, the deal with that is it takes kind of a long time for us to kind of activate those fat burning pathways, about 30 minutes before we start tapping into those fuels. And really, we think by the time you reach 60, 70, 80 minutes of exercise, that's really when fat metabolism is going to kind of ramp up. So again, a lot of our athletes aren't going to be using a lot of fat, honestly. If you're doing something kind of on that shorter, high intensity end, carbs are going to play a more important role. If you're working with endurance athletes, maybe we're having them do, a 90-minute run, or, you're a soccer player and we're playing, over 90 minutes, or your practices are lasting that long where they are really doing exercise kind of throughout that whole entire practice, then we're going to start to see more fat usage as we kind of increase that duration. Okay, so let's talk about carbohydrates. Carbohydrates, again, we can consume these in something called a polysaccharide, which is like a long chain of carbohydrates. And once we take in those carbohydrates, that long like strand of carbohydrates, we're going to convert it into its most basic unit, which is known as glucose. And again, glucose is kind of like a one singular sugar molecule that we're going to use in these different energy pathways that we'll talk about. Now, when we think about the calorie content of carbohydrates, again, this is kind of dipping a little bit into sport nutrition. So for some of you, this will be a little review, and for others of you, it'll be more of a preview. But essentially, when we think about carbohydrates, you have about 4 calories per gram. Okay, so 1 gram of carbohydrates when you eat it is equivalent to 4.1 calories. Okay. And we have about 2,500 calories stored within the body, maybe more like 2,000, really depends on the person. We'll talk about some of those factors a little bit later. But essentially, that's about how much we have within the body. And as we said, glucose is going to be converted into ATP, and ATP is going to serve as kind of the fuel for both the muscles and the brain. If we have extra glucose, so again, let's say I use those dollar bills to kind of fuel out my muscles, fuel out my brain. If I had some extra of that, I can convert it into a storage form of sugar, which is known as glycogen. And glycogen can be stored in the liver. It can also be stored right in the muscles. And that's going to be great if I'm an athlete that is doing exercise that's 30 minutes or less, where I'm going to need that high intensity fuel kind of right away and have that readily available. So that's good to have those fuels kind of filled up. Okay, other things to note about carbohydrates. Again, we're going to have that storage form of carbohydrates, which we said was glycogen. We said that glycogen is going to be stored both in the liver and also within the muscles. And when we're ready to use it, we can convert it back into glucose, which we said glucose was like the singular or like the smallest. It's like one molecule of sugar. Think of it that way. We can convert it back into glucose when we're ready to make more ATP. And the cool thing about metabolism is this is super dynamic. So again, we're kind of always either putting things into storage, taking things out. So again, we got a lot of things going on in here, a lot of moving parts in order for us to kind of maintain homeostasis within those sugar levels, and again, allow us to provide energy for these changing demands. So again, if I go from sitting to running, I can kind of quickly make that transition and get those sugars out of storage and get them ready to be used in the form of ATP. So again, we said that glycogen was kind of our storage version. Glycogen is like many glucose molecules linked together. And again, we must rely on the consumption of sugars or the consumption of carbohydrates in order for us to replenish those. So for example, let's say I go to soccer practice and my soccer practice is 2 hours long, and I burn through a lot of what I have stored, right? So again, let's say I'm burning 600 calories an hour and it's a 2 hour practice. Okay, well, I've really dipped into a lot of these. So in order for us to replenish those or kind of refill those storage bins of sugar, I need to make sure I'm consuming those carbohydrates in order to make that happen. So when we think about fats, these are great options for us in terms of serving as an efficient substrate. So they are very good because we can store a large amount of calories in the form of fat within the body. They have about 9 calories per gram. So again, when we think about density of energy, fats are kind of our best option in terms of calories per gram. So that's a great bang for our buck if we're looking to have a lot of energy. Again, certainly we can appreciate that this can become very problematic when we overconsume fats, which could lead to an excessive amount of body fat stored, and obesity, and some of those types of issues. So as I mentioned, it's very easy for us to store nutrients in the form of fats. So we have about 70,000 calories of fat stored within the body. And again, that's probably enough calories to do quite a bit of exercise if it were easy for us to mobilize and use these. However, it is a little bit more challenging. We have to do an extended or prolonged amount of exercise in order for us to activate and mobilize these nutrients. Okay, so let's take a look at when we're going to use fats. So fats can serve as a fuel source for prolonged exercise. Again, if we get above like 80% intensity, it will actually shut off the fat utilizing pathways. So again, we want to keep that exercise intensity a little bit lower in order for us to actually mobilize and use these fats. So we're going to get a high net ATP yield, but a slow ATP production. So what does that mean? It means that this process of breaking down fats and converting them into ATP isn't going to be very powerful. Okay, so again, if we're looking to do something kind of maximally, like running up a hard hill or lifting a large amount of weight, like in a squat or something along those lines, we're not going to be able to produce enough ATP fast enough with fat as kind of our backbone. So fat's great for kind of a lower or moderate intensity exercise where maybe I don't need as much ATP quite as quickly. So how does this work? We've got what's called a triglyceride, and that's kind of our storage form of fat. And we can break down that triglyceride into free fatty acids and a glycerol backbone. And that's going to allow us to do something called beta oxidation, which we will talk about here coming up. So only free fatty acids are used to make the ATP. That glycerol backbone can be kind of recycled and used for a variety of other tasks. So here we can take a look at our body stores of fuel associated with energy availability. So we've kind of got it divided up where we're looking at carbohydrates on the top and then fats at the bottom. And when we think about, excuse me, when we think about carbohydrates, we can store them in the form of glycogen. And again, glycogen is going to be kind of like a long strand of simple sugars kind of linked together. And we can store some in the liver, approximately 400 calories worth. We can store some in the muscles, and that's about 2,000 calories worth there. And then we also have a small amount of glucose kind of floating around in the bloodstream. And that's, look how small that amount is, only 62 calories there. Again, remember that these metabolic pathways or bioenergetics is going to be very dynamic in nature. So again, if we're using, let's say we're burning 600 or 700 calories an hour during exercise, look at how much calories we have just floating around, only 62. So what that tells us is that we're very good at being able to get things out of storage and put them into the blood in order for us to utilize them. So again, a lot of dynamics in terms of what's happening from a conversion perspective here. Here you can look at fats, and you can see we have got subcutaneous and visceral fat. Subcutaneous fat is the fats underneath your skin. Visceral fat's going to be the fat like kind of surrounding the organs, in the like thoracic region, things like that. And this will account for the majority of the fat that we have stored, about 70,000, 73,000 calories worth. And then we also have a little bit that's stored intramuscularly. So we do have some fat that's going to be stored inside the muscle, accounts for a small amount, about 1,500 calories there. So again, we can see that our potential, we would prefer to use fats over carbohydrates. And as we become more trained, we become better at utilizing fats as a fuel, just simply based on the quantity available. So we have much less carbohydrate available in comparison to the amount of fat we have available. Okay. So we've spent a lot of time talking so far about carbohydrates and fats, and we haven't mentioned proteins a whole lot. So when we think about proteins and their role as it relates to energy breakdown or substrate utilization, we don't want to use proteins. So proteins are going to kind of only be used in a few scenarios. One's like starvation. Um, Protein gives us about 4 calories per gram. And essentially what happens is we're going to take a protein and we're going to convert it into sugar in a process called gluconeogenesis. And the name, I can kind of break it down for you here. Gluco means sugar. Neo, think like neonatal. That means new. So new glucose. And then Genesis, the Genesis story is the creation story in the Bible. And so Genesis means to create. So gluconeogenesis is the creation of new glucose. So basically what we're going to do is we're going to take those amino acids or those protein molecules and convert them into a new glucose molecule. We can also take those proteins and convert them into free fatty acids through a process called lipogenesis. So again, lipo means fat, genesis means to create. So we're creating new fats. Again, not ideal, but this is what could happen if we overconsume protein. I think a lot of times people think like the overconsumption of sorry, protein isn't a big deal, but in fact it is. We can convert those proteins into fats, which just leads to an increase in fat storage. So again, something to kind of think about when we think about what calories we're consuming. Okay. Again, we can, as I mentioned, take this protein, turn it into a fat, and be able to store it for energy or store it for later use. Okay. As mentioned, can be used for cellular energy substrate if needed. So this chart's nice because it just kind of shows you the relationship and kind of the complexity of each of these substrates that we can use and the different pathways that we can utilize in order for them to provide us with ATP. So here you can see food intake at the top, and we've got our fats, we've got our carbohydrates, and we've got our proteins. And as we follow the arrows down, it kind of shows you what some of those different fates can be with each of those substrates or each of those macronutrients. And again, we'll talk about this more in sports nutrition, but to kind of give you a little bit of a preview here, you've got proteins that are going to be broken down into amino acids, and those amino acids can provide us with some nutrients for metabolism. As previously mentioned, we would prefer not to do that unless we absolutely have to. And in reality, we're spending about 10 to 15% of our metabolism will come from proteins, just kind of by default. But again, we would prefer not to. If we move over here to the middle, we can see that carbohydrates are certainly the most versatile option in terms of fuel. So we're going to take those sugars or those carbohydrates and break them down into glucose. If we consume a lot of glucose and we don't really have a great need for them from a energy utilization perspective, we can do something called lipogenesis, which means we're going to take sugar and turn it into fat, and we'll store those in the form of fat. We can also store some sugar in the form of glycogen, and again, we talked about we can store those both inside the muscle or intramuscularly, and we can also store some within the liver. We can also put a small amount of glucose into this, what we call a glucose pool, and that glucose pool is going to allow us to kind of have a readily available supply of glucose that we can use for those different metabolic processes that are happening right now. If we slide over and take a look at fats, fats are going to be consumed in the form of triglyceride, and we'll break those down into free fatty acids with a glycerol backbone. Free fatty acids are the molecules that we're going to utilize, and we can either use those for metabolism as mentioned, or we can store those if we are over consuming them. Again, a lot going on here, and pretty detailed when we think about the complexities that occur in order for us to take those foods and the different fates that those nutrients can have based on our needs and based on what it is that we've already consumed as well. So just kind of really interesting to think of how intricate this really is. So again, when we think about energy production in the form of ATP and taking those macronutrients, those carbs, those proteins, those fats, and kind of breaking them down into ATP, there's lots of factors that are going to be important in controlling how much energy we are producing. So energy release is going to be at a controlled rate based on several factors. Those factors include substrate availability. So how many of those nutrients do we have available, right? So again, if I'm doing high intensity exercise, but I don't have carbohydrates available, well, that's going to create a problem for us in terms of providing us with those metabolic processes or with those metabolic pathways, okay? So again, thinking about how much of that fuel have I given myself and the timing of that as well. Enzyme activity within the metabolic pathway. So again, think of an enzyme as kind of like a coach or a factory worker, right? It's going to allow us to improve the efficiency of a particular process. Okay, so how many enzymes I have, how many coaches I have, you could think of it that way, how many factory workers do I have, is going to speed up my ability to complete that process. Okay, so as I mentioned, enzymes are going to, again, really help us convert products from one form to another. Okay, so again, when we think about metabolism in kind of a general view, we're going to take like the glucose molecule and we're going to break it down into something else. And there are several different processes or steps that it will have to go through in order for us to get it from glucose to that ATP. And enzymes are going to help us kind of speed up that process. So more enzyme activity will result in more product. Okay, so again, enzymes are going to lower the activation energy for a chemical reaction. Basically, what that means is it's going to make it easier for that process to occur, right? So it's going to kind of help speed up that process and help it occur with greater ease. So again, think of it like a coach, right? So a coach's job in some regards is to help our athletes do things with better efficiency or greater ease or maybe faster, something along those lines. So again, that's kind of what an enzyme is going to do within this realm. Okay. Enzymes are going to have a suffix or end with ase. So again, that's kind of how you know it's an enzyme, is if it ends in ase. So for example, lactase or maltase is the enzyme that's going to break down certain portions of sugars into something else. Okay. ATP, for example, is going to be broken down by ATPase. So again, that's the enzyme that's needed in order for us to break down the ATP and get the energy as we are kind of releasing that. So again, now we want to kind of introduce, we've talked about those substrates, we've talked about kind of some of the key elements that are going to be important in understanding the rate of metabolism. Now let's take a look at the energy systems that we have. Okay, so similar to what we talked about with glucose in the blood, we have a limited ATP storage, right? So there's very, very little amounts of ATP stored within the body. And again, kind of interestingly, if we think of this as like the dollar bill, what I'm saying is we don't have a whole lot of dollar bills. That doesn't mean we don't have money in the bank. We just don't have those dollar bills handy, right? It kind of like, I would say like reality now. Like you might have money, but most of us don't carry a bunch of cash around, right? But we can have access to that pretty easily through our debit cards, maybe through a checking account, credit card, etc. Even Venmo, things like that. So we have these different outlets where we can get that money, but we don't have a bunch of cash just kind of hanging around. So what does that tell us? Our body must constantly be synthesizing new ATP. Again, even though we don't probably have a lot of cash laying around, we're still spending a lot and we're still making some. So we've got direct deposit. We've maybe got some direct like withdrawals for your like your car payment or your insurance or whatever it is, so we can kind of have those things happening without us actually having a transaction of cash money, right? So basically that's what's happening within the body as well. We're constantly producing or manipulating or sliding things around in the money world in order for us to be able to do the things that we want to do. Okay, and we have three different pathways that we can use. So again, think of this as like your savings account, your checking account, and maybe you have money in stocks or something along those lines. So we have three different pathways where we can get money from based on the situation. Okay, so the ATP PCR system is going to be our fastest system. Maybe we would consider this your checking account, right? It's very easy for us to get money in and out of there, and we can transfer that money like pretty simple. Okay, the glycolytic system is kind of our intermediate system. This is going to be a little bit harder for us to get money out of this. So I don't have a good example. I'm gonna have to get really creative with my financial examples here. I can't think of a good example here, but it's gonna take us a little bit longer. It's a little bit harder for us to get money out of here. Maybe it's like a CD. So we have more money available here, but it's gonna be a little bit harder. It's a little trickier for us to get this money out. And then lastly, the oxidative system or the aerobic system, this is the hardest for us to access. So maybe this is some sort of, I've invested in a property or something like that. So I have that money available, but it's in the form of an asset right now. So it's a little bit harder for us to really manipulate and move that around, right? So again, that was my stretch for an example of kind of how these energy systems work. Now, let's start by kind of understanding how we break down that dollar bill. Okay, so again, how do we break down ATP? So ATP is short for adenosine triphosphate. So basically what it is, I have an adenosine backbone, and tri means three. So I have three inorganic phosphate molecules hooked on to this adenosine molecule. Okay, so that's what ATP is. And in order for us to get that energy, all I need to do is snip off one of these high energy bonds from the ATP molecule. Okay, so here's my ATP molecule. This is like a zoomed in version of it. It's the same as this down here on B. And what I want to do is I'm going to use the enzyme ATPase to help me snip off one of those phosphate bonds. And as a result, I'm going to end with ADP, or adenosine diphosphate. Di means two, so now I have two phosphate bonds hooked onto the adenosine molecule. And I have a free-floating phosphate molecule. And the snipping of that bond caused us to liberate energy, okay? And this is what we're after here, Okay, so again, it's through the cutting or the snipping off of that phosphate molecule that I'm able to release energy and be able to kind of harness that and utilize it for different processes within the body. So that's the most basic thing we can do in metabolism is take that ATP molecule and break it down into an ADP molecule, right? So when we think about this ATP PCR system, we have to add another layer to it, right? So again, the ATP to ADP is kind of the most basic. We have another step we can add into the mix here in order for us to create this phosphocreatine system, okay? So a little bit about the phosphocreatine system. This system is going to be very fast. It's going to be very powerful, which means we are able to generate a lot of energy from the system. And we're able to do it very quickly. However, I guess two cons with this system. Number one, it can only use carbohydrates as its fuel. And number two, it gets fatigued pretty quickly. Okay, so it can only last us maybe like 10 to 15 seconds total, depending on the individual, depending on their fitness, things like that. Okay. So what is my ATP yield, or what is my, how much money am I getting out of this? I can get 1 mole of ATP for 1 mole of phosphocreatine. Okay, and again, that you're probably like, what the hell does that mean? Again, we'll kind of compare and contrast these energy systems as we move through, so that we can get a better understanding of like what is the energy yield for each of them. As I mentioned, very short or very quick system, very powerful. It can last anywhere from 3 to 15 seconds. 15 seconds is quite a bit. I would say the average untrained individual is going to last about 10 seconds. Most of the athletes that we work with are going to be maybe more like 12 seconds if you are an anaerobic athlete. So, for example, baseball, softball, football, sprinter, or something along those lines are going to be very well trained in this system, and maybe they're going to last about 12. And then you think like Olympic caliber athletes, they're going to be even more than that, maybe like 15 seconds total. Okay. Because these ATP stores are limited, this pathway is kind of constantly being used in order for us to regenerate and reassemble ATP. Okay, so let's take a look at how this kind of works. So again, I'm going to basically take this PCR unit, which is phosphocreatine, and what I want to do is I'm going to take off this phosphate molecule from the creatine and hook it onto the ADP that I had before in order for us to recycle the ATP. Okay, and I've got an image of this to kind of explain in a little bit better detail. So it's going to help us replenish ATP stores during rest as well. So again, if I am somebody who does, let's say, a lot of strength training, I'm going to be constantly breaking down ATP during my lift. Let's say I did a set of 6 on the squats. Okay, so again, if I'm doing 6 reps while squatting, I'm probably not completely depleting the ATP system, because that'd be a pretty short amount of time to be exercising in that one singular set. However, during my rest period, I'm able to kind of recover that muscle with ATP so that I'm ready to do another quality set afterwards, like, in another minute or two to 3 minutes, something like that. Okay, so it's going to help us to recycle recycle the ATP until it's used up, as mentioned. Okay, so this kind of shows you what's going on. So again, we had ATP that we were going to break down into an inorganic phosphate and ADP. Okay, so basically what we're going to do is we're going to use this phosphocreatine. We're going to pull off the phosphate molecule. We're going to combine it with the ADP, and that's going to help us to regenerate ATP. Okay, once I have this ATP again, I can then use it and break it down into ADP and phosphate. Then I can grab another phosphocreatine molecule. I can nip off that phosphate, hook it in with the ADP, and then I'm going to have creatine as kind of like a waste product at that point. Okay. Again, how does this kind of work? This shows you the relationship between ATP and phosphocreatine. Okay, so again, for those first like 2 seconds, for example, we're using pretty much just the ATP that we have stored in the cell. And then as we continue on from like 2 seconds all the way down to like 10 to 12 or whatever it is, right? I'm able to draw more on that phosphocreatine portion. So for example, let's say I am a shot putter. Okay. So throwing the shot put isn't going to take very much time, right? Certainly I need a lot of power and I need some skill and different things like that in order to throw it far. However, the amount of time that it takes me to complete that task is very short, right? So we're looking at just a few seconds. So again, I'm probably only really using that front end of the system, right? I'm only using this portion of the system. Okay. Now, if I were to do something like run a 100-meter dash, okay, maybe let's call it between 10 to 14 seconds, depending on, male, female, what level we're working with. But those first few seconds of that 100-meter dash, I'm really just relying on the ATP. As I slide down through the race and get to like 8 seconds or so, I'm really heavily relying on that PCR portion of the system in order for the system to continue to fuel me so that I can maintain my speed and velocity throughout the rest of that race. Okay, so how does this kind of work, right? So we're thinking about control of this system. And we're thinking about control of this system through an enzyme known as creatine kinase. And creatine kinase is going to be the enzyme that's going to be responsible for taking that phosphocreatine and nipping those apart, right? So it's going to break off the creatine and the phosphate molecule into two separate pieces so that we can take that phosphate and then dump it onto the ADP. Okay, so phosphocreatine breakdown is catalyzed by CK or creatine kinase. Okay, so if it's catalyzed, that means it's kind of like sped up. So the amount of CK or the amount of creatine kinase is going to control the rate of ATP production in the system, right? The more creatine kinase I have, the more I can produce in terms of ATP within that given amount of time. Okay. And it's a negative feedback system. Okay. So again, a lot of us as coaches are trying to upregulate the system, right? I want to have more CK so that I can do more work and move from being able to hold that speed for 10 seconds to holding that speed for 12 seconds, right? So again, with negative feedback, the more I use that system, the more I can kind of upregulate that. So again, when we think about who would benefit from upregulating the system, athletes who use the system regularly. So this negative feedback is great because we're going to adapt to this system and allow ourselves to kind of upregulate these processes so that we become more efficient, right? So football, baseball, softball, throwers in track and field, high jump. So those are all examples of people or athletes that are going to be pretty highly reliant on this particular system in order to be successful in their sports. So again, when those ATP levels drop, the CK activity is going to increase or be enhanced, right? So again, as I enhance my need for CK, I can produce more within my body and therefore kind of upregulate the system so that I can get better at that. And again, the way we do that is through chronic, consistent, good training, right? So again, whether that's in the weight room or if it's doing some different accelerations or different activities where I can really activate and stimulate the system, that's going to allow me to upregulate that CK activity and therefore allow my athletes to improve this particular system. And again, kind of interesting, and I'm getting ahead of myself, I know that, but it is so fun to look at an athlete and be able to figure out where their strengths and weaknesses are. For example, I coach distance running, and I have a kid right now, a high school kid that is on my team that you could give him a 10-mile, 12-mile run. He'll crush that. He loves that. He's so good at being able to hit a consistent pace and really work his aerobic engine. Now, if you ask him to put any type of weight on the bar for a squat, he's not good at that. He can't squat a lot. He doesn't have a lot of strength. you ask him to do like a 50-yard sprint. He's getting beat by pretty much everybody on the team. That would be, a little more, I would say, athletic than him. So again, upregulation of the system would help him a ton to gain more speed, if we can get him to, really deplete the system and then try to upregulate that. So again, a lot of this is genetic in nature, but a lot of it has to do with how we train. So again, this kid is doing a ton of aerobic work, which we'll talk about a little bit later. So he's really unbalanced, right? He doesn't have a lot of strength in this particular system because it's not something that he is constantly stressing. Okay, so next we're going to move forward and talk about the glycolytic system, which we said was kind of that intermediate system. And essentially what we're doing in this system, sorry, this picture is a little bit small. I'm not going to make you memorize all of these configurations or anything. I just wanted to show you the complexity of how the system works. So with the glycolytic system, or with glycolysis, what we want to do is we're going to take glucose and we're going to break it down through these several intermediates into pyruvate. Okay. Again, I don't need you to memorize all these things, but know that there's an enzyme that's listed in green that kind of goes along with each of these steps. And we're going to convert that glucose into these various intermediates before we eventually get to our final product, which is pyruvate. Okay. This is anaerobic in nature. Okay, so this process so far does not require oxygen. Okay, so we're going to take that glucose, convert it to these multiple different levels, and then eventually we get to our final level, which is pyruvate. What do we get out of this? Again, on the previous energy system, we said that we were going to get about 1 ATP per 1 mole of phosphocreatine. Here you can see our energy gain is a little bit greater. So we get 2 to 3 moles of ATP per 1 mole of substrate, and 1 mole of substrate comes from 1 singular glucose. How long does the system last? So on the previous system, we said probably up to about 15 seconds. This intermediate system will last between 15 seconds to 2 minutes. Okay. Again, we're going to break down glucose through the process of glycolysis, as I mentioned. Okay, a little more about glycolysis. So again, we're going to use glucose, as was mentioned on the previous slide. We can also use glycogen as our kind of our starting point. Okay, and regardless of which option I choose to start with, the first step is to convert those items into glucose 6-phosphate. Okay, the pathway starts with glucose 6-phosphate and ends with pyruvic acid, or pyruvate, as was mentioned in the previous slide. Okay. Again, I'm not going to test you on the chemical makeup of each of these intermediates or the names of all of these enzymes, but do know that it is complex. So we are going to rely on 10 to 12 enzymes in order for these reactions to occur. Where does this take place? So this is going to take place in the cell cytoplasm, which is kind of just like an open area inside the cell. It's kind of like a gel-like material. And again, that isn't important yet, but it will be as we get to kind of that next energy system here that's coming up. So the ATP yield, we're going to get 2 ATP for glucose and 3 ATP if we break down a glycogen molecule. Okay, so a little bit more than what we were getting in the previous system. Now, some of the cons of this system. We don't get a whole lot of ATP. We're only getting 2 to 3. You'll see in the next systems, we're going to get a shit ton. We're going to get way more ATP out of the deal here. So again, a low ATP yield, it's not really that efficient for us to use this in terms of that substrate. So again, taking a sugar and breaking it down through this pathway kind of takes a long time, and it's inefficient, right? We got to do 10 different things to just get like 2 to 3 ATPs. Well, in the other system, we only had to do like one thing. So it was way faster with that ATP PCR system. So it's not great, but again, I'm going to talk about why we use this here coming up. We don't need oxygen, so that I would consider that a pro. because we're going to eventually get to exercise that's so intense that I need to do everything. I need to use all my energy systems. And so the lack of oxygen allows the system to continue. However, the bad news with that is if I don't have oxygen, I'm going to take my pyruvate or my pyruvic acid and convert it into lactic acid. And that's bad news for us because lactic acid comes with a hydrogen molecule, which is acidic and causes us to have that like burning sensation, or kind of like when your legs feel like they're bricks. When you're trying to do something, that's going to be because of this waste product. And we'll talk more about that here in just a little bit. Okay, so again, the other bad thing with lactic acid is it's going to impair glycolysis and muscle contraction. So again, it causes us to feel like really heavy legs, or that burning sensation that you get when you do really high intensity exercise. What are the pros of this system? It allows the muscles to continue to work even when oxygen is limited or not available. So again, it's going to allow us to kind of maintain an intensity with a pretty high cost, because that lactic acid does not feel good. We don't like that. We don't like how that feels, both from a physiological perspective and from a mental perspective as well. It's very hard for us to make ourselves or to make our athletes continue to push through when something hurts, because it goes against our kind of our common sense. It goes against those survival skills that we have, right? In reality, we want to avoid painful situations. That's how our ancestors survived. And so, what we're asking our athletes to do is the opposite of that. And so it goes against the grain of what is kind of embedded in our minds and embedded in our heritage. And it hurts, right? It doesn't feel good. So again, teaching kids to push through that can be really, really tough as coaches because of the pain associated with that lactic acid. Okay. The good news, it permits shorter, higher intensity exercise than what we can get out of the next energy system, which is the oxidative system. Now, glycolysis really gives us two options, right? So I've kind of lied to you so far. Glycolysis is going to take glucose and convert it into pyruvate. Okay. If I have no oxygen available, I'll take that pyruvate or that pyruvic acid and convert it into lactate. Again, I said lactate was kind of bad, right? And it's not that it's necessarily bad, it's that it is a limiter for us, right? As I produce lactate, there's only so much lactate my body can tolerate. Okay, so the more hydrogen, the more lactate that I have, I'm working on limited time that I can kind of maintain that intensity, right? So again, as I start accumulating that lactate because I have no oxygen present, I know I can only maintain that intensity for maybe a minute, maybe 2 minutes longer. Okay, so for our best athletes, maybe 2 minutes I can hold that intensity, or increase intensity above and beyond when we start accumulating that lactate. Okay. However, if I do have oxygen present, this pyruvate is going to enter the Krebs cycle, which is that oxidative pathway. Okay. So that will be the fate. That's our preferred fate for pyruvate. We would like it to go to the Krebs cycle because I can get more ATP out of it, and I don't have to produce a waste product that causes pain. So again, preference is always going to be the easiest route that we can take, and the easiest route from a waste product perspective is this oxidative pathway, and we will do that through the Krebs cycle. Okay, so this kind of shows you the relationship between these different processes. So here you can see glycolysis occurring. Again, we said glycolysis is going to occur in the cell cytosol or cytoplasm, which you can see here. Again, as we break down one glucose into pyruvate, we were going to get 2 ATPs. If we broke down a glycogen molecule, we were going to get 3 ATPs. We're also going to get some NADH, and NADH is nice because think of this as like a what are those called? Like the Kohl's Cash that you get when you buy clothes at Kohl's or whatever. They give you like a $10 off coupon for the next time that you come in. Okay, so we're going to be able to cash in our Kohl's Cash here a little bit later on. Okay, so this pyruvate, if we don't have oxygen available, it'll produce lactate through this anaerobic pathway. If we do have oxygen available, it's going to slide on into the Krebs cycle. As it's converted to acetyl-CoA, we can enter into the Krebs cycle, which will occur inside the mitochondria. Okay, so this is the second step of the aerobic pathway. So step 1, glucose to pyruvate. Step 2, pyruvate to acetyl-CoA and into the Krebs cycle. Step 3 will be NADH to the electron transport chain. Okay, and this is going to be our money maker in terms of ATP production, this electron transport chain. Okay, so again, we said that lactate was problematic because it's going to create acidity or change our pH and affect homeostasis within the cell, making the muscle feel like it's kind of like burning. So 3 different things that can happen here. So muscles can utilize lactate in 3 ways. So number 1, it can be taken by the mitochondria in the same muscle and be able to be oxidized. So we can take it into the mitochondria and kind of convert it into a product that we can use in the Krebs cycle. It could also be transported to other cells where it can be used, and it can recirculate back to the liver and be converted into pyruvate and create glucose through a process called gluconeogenesis. Okay, so let's move on and take a look at the oxidative system. Again, oxidative tells us that we need oxygen, so therefore it's aerobic in nature. Aerobic means that we need oxygen in order for the pathway to work. And here, check out this bang for our buck. So we're going to get 22 to 23 ATP per 1 glucose within the aerobic system. Okay, we're going to get over 100 ATP for 1 fatty acid. In fact, I want to say it's 129 ATP per 1 free floating fatty acid. Okay, how long does the system last? 2 minutes or more with a steady supply. And it's going to occur within the mitochondria in order for us to complete this pathway. Again, here you can kind of see that the same image as before, and now we're going to kind of focus on what's going on here. So step 1, glycolysis, step 2, the Krebs cycle, and step 3, electron transport chain. Okay. Again, not going to ask you to memorize any of these configurations, just kind of want to show you what's going on here. Step 1, glycolysis. Glucose is broken down into pyruvate. We get some ATPs out of the gig, and now this is occurring in the cell cytosol or cytoplasm. Okay. And step 2, we're going to move those pyruvate, convert them to acetyl-CoA, and those acetyl-CoA are going to enter into the Krebs cycle. Okay. And then step 3, we're going to use the electron transport chain, which also occurs on like the edge of the mitochondria in order for us to get our greatest bang for buck within the electron transport chain. Okay. So oxidation of carbohydrates. So let's take a look. So glycolysis, again, we said can occur with or without oxygen. With oxygen, we're going to feed that pyruvate into the Krebs cycle with acetyl-CoA. Without oxygen, we're going to take that pyruvate and turn it into lactate and release that with a hydrogen molecule, which creates some acidity. The ATP yield is the same no matter which of those pathways you choose. So whether you go aerobic or anaerobic in nature, you get the same ATP out of glycolysis. The major negative when using the anaerobic side is that we're going to produce hydrogen and lactate. Same general steps. Again, it just has to do with kind of what is the end fate of whatever the last step is, that pyruvate molecule. Okay, so again, pyruvic acid or pyruvate is converted into acetyl-CoA and will enter into the Krebs cycle if it's aerobic. Here is the beautiful Krebs cycle. So you've got your pyruvate that's converted into acetyl-CoA, and then we enter into this cycle where we're going to produce, as I mentioned, some NADH. We're going to produce FADH. We're also going to produce some ATP. Okay, FADH and NADH, again, think of them as like Kohl's Cash. They're like coupons that we can use to get energy a little bit later on. I don't know what new you saw here, but essentially we're taking those NADH and FADH molecules and we're going to use them or trade them in for energy in the electron transport chain, which is coming up here. All right, electron transport chain is freaking cool. So now I can take NADH and FADH, and basically what we're doing here is we're sliding H molecules down their concentration, or I'm sorry, across this membrane to out here. So you can see all the H molecules moving out here. And then those H molecules are going to slide down this ATP synthase pump and use that pump. We're going to use the energy of them sliding down this gradient, and it spins kind of like a little tilt-a-whirl or Ferris wheel or whatever you want to think of it as. And the spinning sensation is going to allow us to produce ATP here. And this is how we get 90% of the energy that we have. Okay, so each, as I said, those NADH, which you can see here, we can trade that in for 2.5 ATP. So each NADH gives us a net total of 2.5 ATP, and each FADH gives us a net of 1.5 ATP. Okay, so again, that's kind of your net gain with those Kohl's Cash coupons that we're going to be able to trade in as kind of like a rebate. Okay, so we think about oxidation of carbohydrates in terms of energy yield. One glucose molecule at the end of the day can give us 32 ATP. One glycogen gives us 33 ATP. Again, that kind of breaks down those net totals. So again, with glycolysis, you get 2 or 3 ATP out of it. Krebs cycle, you get 2 ATP or GTPs. And you get 10 NADHs, which again, we said each NADH was worth 2.5 ATP when we entered those into the Krebs cycle. You had 2 FADH, and those gave us 1.5 each, so that's another 3, and we add those together, and that gives us that total of 32 to 33. Okay. Again, this just shows you the exact same thing. So again, from glycolysis, I get 2. I also get some NADH up here, which gives me 5. I get some NADH down here, which gives me 5. I get NADH down here, as well as FADH, and then an additional GTP or ATP out of the Krebs cycle as well, which gives us a net of 32. Okay, so we've talked about the energy yield associated with carbohydrates, and now we're going to take a look at what happens with fats. And fats, our major kind of fat source is known as triglycerides. And again, we can store these in a variety of places within the body. And basically what we want to do is we're going to take this triglyceride and break it down to free fatty acid, and we want to bring that into the muscle. Okay, so again, the amount of free fatty acids that are in the muscle is highly dependent on this concentration gradient. And again, think of this as just kind of like supply and demand. So if I start using fat as a fuel source in particular muscles, that's going to increase the need for more fat. And so therefore fats will come in kind of via this concentration gradient that's mentioned here. So when we think about kind of the pros and the cons of fat oxidation, the good news is that we can get significantly more ATP out of the gig. However, the major con is that it's going to be a slower process in comparison to the breakdown of sugars. So if I'm looking for energy quickly, it's better to choose carbs. If I'm looking for a lot of energy, but I can kind of do it at a slower rate, then fats are a better choice for us. Also important to note that fats use more oxygen to break down. And the more carbons that I have in my chain in the free fatty acid, the more acetyl-CoA I can produce. And the process known as beta oxidation, which I think is on the next slide, is basically taking a free fatty acid molecule and breaking it down into multiple acetyl-CoA molecules. Once I have these fats broken down into acetyl-CoA, the acetyl-CoA can then enter into the Krebs cycle and will kind of follow the same pathway that it would if it came from like a sugar, for example. We also can increase the number of electrons that we have as it relates to fat breakdown. And again, this is going to be beneficial for, excuse me, for the electron transport chain, which is great. And again, both of those factors together, the more acetyl-CoA and an increase in electrons would allow us to increase the amount of ATP that we produce from one fat molecule. Okay, so as I mentioned, beta oxidation is the process by which we take a free fatty acid kind of strand and chop it off into acetyl-CoA molecules. So the number of acetyl-CoAs that we get out of this is dependent on how big that chain really is. So generally, like a good rule of thumb, if I have a 16 carbon free fatty acid, I'm going to get 8 acetyl-CoAs. Again, just to kind of compare this with what we see with sugars, I get 1 glucose gives me 2 acetyl-CoAs, and with 1 free fatty acid, I'm getting 8 acetyl-CoAs. So again, a greater bang for our buck in terms of the net ATP gain that we get out of this breakdown process. However, as was mentioned, fat oxidation does require more oxygen. However, it will yield a greater amount of ATP later on. Okay, so let's take a look at what's going on with the oxidation of fats as it relates to the Krebs cycle and the electron transport chain. So as we said, the acetyl-CoA will enter into the Krebs cycle. And from there, it will kind of do the same exact thing that what we saw with the glucose molecules. However, it is important to note that different free fatty acids do have different numbers of carbons, and so therefore there is a little bit of variance in terms of how many acetyl-CoAs I get per fat molecule. What about the oxidation of protein? So let's take a look at this a little bit. Energy yield is not easy to determine with protein oxidation, and the reason for that is number one, it contains a unique element in nitrogen, and so nitrogen can make things a little bit muddy, but also I guess probably more important from a practicality perspective, we're not really using protein as a fuel source. Protein has a lot of other unique characteristics, other unique jobs that can't be substituted in with carbohydrates. We can't substitute in for fats either. So again, we're really going to use proteins as a substrate. Maybe about 10 to 15% of the calories that we are breaking down are going to come from protein. And basically what happens with this, two different options. We can convert some of these proteins into glucose, and we can convert some into acetyl-CoA as well. This chart I just thought was nice to include because it gives us kind of an idea of an overview of all of these processes and kind of what's going on here. Again, just super interesting to kind of think about the complexity of these three nutrients and kind of how they all fit together in terms of allowing us to create or produce ATP. Okay, so thinking about the interactions of these energy systems. Again, all three of our systems are going to interact for all activities. So what does that mean? All three systems are working at any given time. When we say like, okay, the ATP PCR system is in charge during, short high intensity exercise bouts, basically what we mean is the ATP PCR system is giving us the majority of our energy during that type of activity. However, we are still getting some energy from the anaerobic glycolytic pathway and from the oxidative pathways, and vice versa. Again, if I'm going to run a marathon, certainly that oxidative pathway is going to provide me with the greatest amount of energy. However, the anaerobic glycolytic and the ATP PCR system are going to contribute a little bit during that type of activity as well, right? So again, essentially what we're saying is all three energy systems are kind of always working, but it's just a matter of who's kind of in charge based on what it is that we are doing during that given time. So this kind of illustrates that. So you can kind of see the difference here with maximal rate of ATP generation, and maximal available ATP. Okay, so again, we think about maximal ATP available. Fat oxidation is our best option because we have like a lot of fat stored. That's not me calling you fat. That's me telling you that you have 70,000 calories of fat stored within your body. And so therefore we've got a lot of ATP available there. Okay, our second best option is carbohydrates in the storage form. Then we go to anaerobic glycolysis, and lastly, PCR system, the ATP PCR system. Okay, very little amount of ATP available there. Okay, here you can think about the maximal rate. So again, when we think about this, think about the maximal ability to produce power. Okay, so ATP PCR system is the most powerful of our system, meaning that we can turn it on and be able to get a lot of energy really, really quickly. Okay, glycolysis would be second, and then carb oxidation through the aerobic pathways and fat oxidation through those aerobic pathways would be third and fourth, respectively. Okay, this is just a nice chart that kind of shows us or gives us the characteristics of each of these energy systems. Okay, so again, here you can see the energy systems on the left side, and we can see the oxygen needed, kind of the overall process, the relative amount of ATP that we can get out of the gig, and the amount of ATP formed per molecule of substrate. So again, thinking about like what's my investment into this system in order to get the ATP out, and then how long can that system kind of function at its highest capacity. Okay, so when you think about the oxidative capacity of a muscle, not all muscles are going to exhibit optimal activity of oxidation enzymes, and therefore we believe that enzyme activity can predict our oxidative capacity or potential, and this has a lot to do with both training status and genetics. Okay, so again, not all muscles have the equal capacities to develop oxidative energy. Again, think about genetic differences, but also training status differences between different athletes or different people. Factors that determine our oxidative pathway, as I mentioned, certainly training is going to play a huge role. So somebody's training status will make a big difference. Also, the type 1 versus type 2 muscle fibers will play an important role in determining the oxidative capacity. So our type 1 are our slow twitch fibers, and we'll have a greater aerobic capacity with slow twitch fibers in comparison to the fast twitch fibers. And then, like we said, genetics will play an important role in kind of like that natural amount, or our ability to adapt to training will be highly related to kind of that genetic element as well. Okay, enzyme activity. So again, the more I use a certain system, the greater the enzyme activity we get from that. So again, those enzymes are going to increase in their numbers and efficiency if we constantly or chronically, I should say, utilize that pathway. So again, the more aerobic work I do, the more oxidative enzymes I have, and the more efficient the oxidative enzymes that I have will become as well. So I mentioned this just briefly, but kind of taking a look at fiber type composition and endurance training. So again, as I said, we have a couple different types of muscle fibers. We have those fast twitch and slow twitch. We also have an intermediate type of fiber. And again, want to take a look at what's going on with that as it relates to endurance or oxidative training. So again, type 1 is kind of those slow twitch fibers, and they're going to have the greatest oxidative capacity. So again, if I train for endurance types of things, we're going to upregulate those type 1 fibers. And again, everybody's got a little bit of a different amount of those, which would allow us to kind of understand the genetic differences that we might see between our athletes. And again, we think about that as it relates to endurance training. Certainly, it is interesting to kind of see how we can give everybody the same workouts. And, you know, we've got some kids that can keep going, keep going, keep going, and other kids that just can't hack it with the, you know, with the endurance type of training. And maybe it's a matter of like toughness. You know, that's one thing that I always think about when I have kids like that. But also, we have to think about, okay, does one type of kid have more of these type 1 fibers, and so therefore they have a greater capacity kind of just naturally, or a greater ability to kind of upregulate what they have, right? So when we think about oxygen needs of the muscle, as the intensity of the exercise increases, so does the need for ATP, right? So again, we need ATP in order to allow us to do exercise. And so as the exercise gets harder, we need more ATP in order to keep that going, okay? So this is going to be responsive, right? So again, as I start to do harder work, as a result, I'm going to then increase the amount of ATP that I'm producing. Okay, so it's going to allow us to increase the oxidative rate of ATP production. When we think about the oxygen needs of a muscle, we know that oxygen has a limited ability to be stored, right? So again, I either have to use what I brought in or I'm going to blow it out, right? So again, we don't have a lot of a strong ability to just kind of hold on to that oxygen until we need it. It's kind of a constantly moving process when we think about respiration. So oxygen levels entering and leaving the lungs will give us an accurate estimate of the amount of oxygen that we have used during that exercise bout. All right. So again, that gives us a little bit of information about the energy systems and ATP as well. And next week, we're going to take this information and then be able to apply it to various exercise tasks and kind of start to understand, what does that look like? So again, we've talked about these energy systems. How does that relate to what I do in practice? How does that relate to how my athletes perform in a game? In a race, in a match, etc. Right? So let me know if you have any questions. Otherwise, I hope you have a great day and we will see you next time.